Michael, you're going to explain it. All right, so here's the next big unit, which is forces. But to get into forces, we really have to figure out how to do vectors, because forces are like the poster child of vector quantity. So we're going to spend a couple of days going through vectors. The first day is what we call the graphical addition of vectors. This is why you need a protractor and ruler, because we're going to draw everything out. Tomorrow we'll do trig functions, okay? So the reason that I spend a day doing like the visual side of this and how you can draw them out is that one year we had like a bunch of snow days, and I skipped the graphical side of it and just went straight into the trig side of it. And it was an absolute train wreck. The kids didn't understand what was going on because they didn't understand the visual side of it. So that's why we're basically going to spend one day on the visual graphing side of it, and then we can start to do the trig function side of it, because otherwise you all don't get the visual part of this. So the forces unit is probably one of the longest units that we're going to have, mainly because we have to deal with friction, inclined planes, net forces, all of this stuff, okay? So it's going to be one of the longest units that we have. So just settle in. It's going to be a long haul, but it's also probably the most important unit that you have, because if you can't do forces, you can't do like electric fields, you can't do magnetism, you can't do momentum. There's a whole bunch of things that you cannot do if you don't understand forces. So that's why it's so important about this. Okay, so this sounds very daunting. The graphical addition of vectors using the tip-to-tail method. It sounds horrible, okay? It's really not. And you all understand the method. I just have to convince you that you already know how to do it, okay? So let me give you a simple example. So the first thing we have to do in this example is establish a set of rules in terms of how we're going to handle angles. So the first rule of vectors is that the positive x-axis is equal to 0 degrees. So if you look at an x and y coordinate system, this positive x-axis will always be defined as 0 degrees. That way, we don't have to guess is 0 degrees 90, straight up, is 0 degrees down, I don't know what that is. So just to make it simple, we're going to define the positive x-axis is 0. And then we're going to measure all angles counterclockwise from that positive x-axis. So this is going to be 90 degrees, that's going to be 180, that's going to be 270, so then like an angle in there might be like 350 degrees. That eliminates negative angles. So don't come in here and say, well, the angle is negative 10 degrees. I have no idea what negative 10 degrees means. I don't know if it's negative 10 here, is negative 10 down over there in that third quadrant. I have no idea what negative 10 is. So that way, by keeping everything on a positive, on a counterclockwise, I don't have to worry about how, Dominic defines negative 10 degrees versus how Michael defines negative 10 degrees. So that way everybody's on the same page and all the angles are just going to be positive value. So the other thing that's going to be different, obviously, is that we're using degrees. Up to this point, we've used like positive and negative because we've only been dealing with in one dimension. Oh, it goes up, it comes back down. Okay? Simple. Well, but things are more complex. Like, okay, hey, I'm going to launch the tennis ball at an angle of 60 degrees. Well, that isn't just a simple x and y coordinate system. How do you deal with angles? And that's how you deal with them, is first off establishing, okay, how are we going to measure things? So everything is measured counterclockwise. So let me give you a simple example. So let's say we're going to have a tug of war, okay? So Sydney is going to be pulling this way with a force of 20 newtons at 0 degrees, okay? It's tug of war. Sydney's gonna be pulling this way, okay? Now, over here, Ryan is gonna be pulling 15 newtons at 180 degrees, okay? So Sydney's pulling this way at 20, Ryan's pulling this way at 15. These are all going to be vector quantities, which means they have to have two things, which are magnitude and direction, okay? So if you just tell me, hey, Sydney pulls with a force of 20 newtons, cool. I don't know which direction that she's pulling, okay? Or if you just tell me, hey, Sydney's pulling at 0 degrees, great. I know which direction that she's pulling, I just don't know with how much force she's pulling. But as soon as you give me both bits of information, how hard she's pulling and in which direction, now that becomes a vector quantity. Now, these could be forces, they could be acceleration, they could be velocities, it could be displacement, it could be momentum, it could be electric fields, it could be magnetic fields, okay? Anything that can be represented as a vector quantity, we're going to go through the exact same process, okay? Nothing changes. This just happens to be forces. So, I got Ryan pulling that way, also vector quantity, 15 newtons at 180 degrees. Now, as this is drawn, this is not the tip-to-tail method. This is a specific type of diagram, what we call a free body diagram, okay? And don't sit there and go, is there one you have to pay for? No. Free body diagrams, we're going to draw them a lot, okay? We're going to draw them a lot. So basically what happens on a free body diagram, you let the object be represented as a dot. It could be a block, it could be a squirrel, it could be the earth, it could be the moon. Doesn't make any difference. You just say, okay, here's the dot that represents the object. Then you draw all the forces acting on that object from a common center. And it could be velocities, it could be displacements, anything that's a vector quantity. Okay, forces are just kind of the quintessential thing. Usually with free body diagrams, it's going to be forces. So all of this allows me to do, I can't solve the problem this way, but what it allows me to do is see what's happening dynamically. And don't think, oh, we're limited to two forces, okay? There might be a third one, okay? Francesca, right?
Francesca.
Okay, Franny. Okay, might be pulling like that, okay? There might be a third person, there might be a fourth person, there might be a fifth person, okay? So don't look at this and go, oh, there's only two. No, you could have 4 or 5, whatever. So, drawn like this, that's a free body diagram, okay? It's just a sketch going, I got this force going this way, I got this force going this way. Now, the actual tip-to-tail method, and this is what you're after, you draw a new X and Y coordinate system. Okay? Draw a new X and Y coordinate system. And then you go, okay, I'm going to draw Sydney's first. Okay? Doesn't make any difference. I'm just going to draw hers first. 20 newtons at 0 degrees. Here's the next critical step. I'm going to imagine that I could take Ryan's vector and physically cut that out. And then I'm going to glue that from the end of Sydney's vector. Okay? So this is why it's called the tip-to-tail method. So all that vector does is tell me where to start a new X and Y coordinate system. So this is new. That's a new point. It's like a new X and Y. So from the end of this one, now I'm going to draw Ryan's coming back like this. Okay, cool. So Ryan's vector is going to be like this. So here's Ryan's, which is 15 newtons at 180 degrees. Got it. Nice. Got it. No worries. Here's the most critical part. Because what you're after is the net effect of these vectors. This is what we call the resultant. Your resultant is the end game of this process. This is what you were after. What is the resultant? Now, what we're going to do is, at the end of this one, come back like this. There's force Ryan. So this is kind of a little bit of an Australian thing. Crikey. So we're going to call it the Roo. Okay? So here's this horribly drawn kangaroo. There's his pouch. There's the tail. There's his feet. Okay? So there's a kangaroo. So the Roo stands for the resultant, which is what you're after, goes from the origin out. Okay? That's why I said it's like the kangaroo. Crikey, that's a ripper. So you're starting here, okay? And you go from the origin out to wherever you end up. So in this situation, I'm going to go from here out to that point. So here's why this is important that you draw it that way. So this resultant is 5 newtons at 0 degrees. So, and this is why I said it makes sense. So Sydney's pulling this way at 20. Ryan's pulling back that way at 15. So the net effect of those two forces added together are 5 newtons at 0 degrees. Makes sense. Now, this is why you have to draw it that way. If you draw it from where you end up back to the origin, then that's technically at 180 degrees. So you would say, oh, hey, Sydney's pulling this way at 20, Ryan's pulling back this way at 15, but we're actually going to go in Ryan's direction, even though he's pulling with less force, which doesn't make any sense at all. Okay? Now, here's another way that you can view this. Okay? Some people like a displacement analogy. So, you start right here. Okay, so I'm going to walk here. I'm going to walk out 20 steps. Straight line, 20 steps. I'm going to get to the end of this, and then I'm going to come back. Okay? And I'm going to stop right here. I was like, oh, man, I'm thirsty. I need something to drink. Okay? So what this does is that this tells you how to get to where I ended up. Okay? So this would be like, hey, Cooper, you need to take 5 steps at 0 degrees to get to where I ended up. Okay? So if you like a displacement idea, oh, I walked here, I came back 15. How do I get from where, how do I tell someone to get from where I started to where I ended up? Okay? Got the idea? Good. Okay. Now, we're going to step it up a little bit. That was as simple as it gets. That was just in one dimension. So imagine that we have a soccer ball. So we have one force being applied of 20 newtons at 0 degrees. And at the same time, it's also kicked, force 2, which would be 15 newtons at 90 degrees. Okay? So imagine that you have Isaac and Son both kicking the soccer ball at the same time. Isaac's kicking it this way, Son's kicking the ball this way. Okay? At the same time. This is not the tip-to-tail method. This is a free body diagram showing all the vectors acting on the system, but it gives you an idea. So clearly, where's the ball going to go? Somewhere between what? 90 and 0. You know that angle has to be somewhere between 90 and 0. Closer to 0, closer to 90. Closer to 0, why?
More force.
That's the bigger force, right? Okay. So this at least tells me, hey, this resultant, I don't know what it is, but it's going to go somewhere in between these 2 points. Okay? So that's the free body diagram sketch. Shows, hey, here's all the things acting on the system. This is a good habit to get into because it at least tells you where to start, gives you a good visual. So here's the next thing. Now we're actually going to do the tip to tail method. So when you're doing this, you are actually going to take a ruler and you are going to measure out like 20 newtons, whatever your scale is. Maybe you let 1 centimeter equal 1 newton, something like that. You are actually going to draw out this line to scale, not a sketch. You're going to draw that out. So you're going to come out here and go, okay, I got this. Boom. So there's my 20 Newton line at 0 degrees. Cool, got that number. Then from the end of this, now I'm going to take that 15 Newton and draw that one. So now I'm going to go like this. Boom. 15 newtons at 90 degrees. And here's the most critical thing. And that's going to be that resultant that goes from that origin out to where you end up. So this is why you have to have a protractor ruler. Yes, eventually we will deal with trig functions. We're not there yet. We'll get there. So you're going to take a ruler or your protractor and you're going to measure that angle. Okay, 18 degrees, whatever that is. Then you're going to take your ruler and you're going to measure the length of that line. So you might say, okay, hey, my resultant is 27 newtons at 35 degrees, whatever that is. So again, here's the basic idea, okay? Isaac starts here. He walks. He gets to this point. He takes the left. He gets there, okay? And he stops, okay? And Dominic goes, man, you forgot your water bottle. Let me hook you up. So he's going to start here and walk in that direction. So this is telling how to get from where Isaac started to where he ended up. Okay? Got the idea? So here's as complicated as it gets. Okay? Here's as complicated as it gets. So we'll go back with the soccer ball. So there's a soccer ball. We have one force, say 20 newtons at 40 degrees. And then we're going to have a second force of 30 newtons at, I don't know, 135 degrees. Okay? So, soccer ball, kicked at the same time. One going at 20 newtons at 40, the other one going 30 newtons at 135. Again, this is not tip to tail. This is a free body diagram showing the forces that are acting on the system. Okay? This is not the tip to tail, just a sketch. So this is where this gets complicated. So what you need to do, this is why some people like to do this on graph paper. So the first thing that you need to draw is that 20 newtons at 40 degrees. So again, you're going to take your protractor, lay it out here. Boom, here's 0. You're going to measure up 40 degrees. You're going to make that mark, and you're going to draw this line. Okay? Done this before. Come over here. Boom, there's 40 degrees. Draw that first vector. There's 40 degrees, 20 newtons. Now, when you draw the next 135 degree angle, this becomes a whole new X and Y system. So when you measure 135 degrees, it has nothing to do with this vector. All this vector did was tell you where it stops, okay? So imagine that you're just starting over, like here's a whole new X and Y system. So when you do that 135 degrees, you're going to put it here like this. You're going to measure around like this, 135 degrees. Make that mark, boom, like that. So don't measure 135 degrees like this, okay? It's not it. You're going to start over from scratch, just like a brand new system. All this did was tell you where to get to the end of the vector. That's all it did. So, I'm gonna measure around 135 degrees, then this. And that's 135 degrees. So, here again, this is the end game, okay? The resultant is the end game. So, my resultant is gonna go from this origin out to, that was horrible. That point. So, when you measure the angle, there's a common mistake that's made. This is not the angle that I want. The angle that I want is back from that initial positive x-axis from where I started, okay? Don't measure this angle, not the story. It's where you started from here, okay? Because I gotta tell Ryan where to go to get to Cooper. And it isn't this angle. Ryan is starting back at that origin, okay? So I'm gonna put this like this. I'm gonna measure it around like this. It's 112 degrees. So maybe that's, I don't know, 32 newtons at 112 degrees. So it would be like me telling you to just draw one vector, 32 newtons at 112 degrees. That's the vector that I want you to draw. That's the net result. Okay? Got it. Okay. Now, sometimes with vectors, we want to like have multiplications of a vector in the sense that you might be told that like vector S might be like 10 newtons at 20 degrees, okay? So there's some, what we can do different things with this. So sometimes we want to double this. So let's say that you're told to draw 2S. So if you're told to double it, that doubling only affects the magnitude and not the angle. So if you were to draw 2S, that's basically saying you need to draw 20 newtons at 20 degrees. So S would just be 10 newtons at 20 degrees. 2S would be 20 newtons at 20 degrees. It could be 1/2 S. If it was 1/2 S, you draw 5 newtons at 20 degrees. So whatever that factor is out in front, all that does is change the magnitude. Now, you can also have this. They might give you negative S and ask you to draw that. So the negative means that you're going to flip it around 180 degrees. So if the first vector was at 20 degrees, then you'd add 180 degrees to it and be over here at 200 degrees, and then you would draw it like this. Now, they might do some wonky things. They might go, negative 1/2 S. So you draw it half the length at 180 degrees opposite of whatever that vector is. So all that multiplications are doing is either telling you, flip it 180 and then alter the length by whatever that fraction is. Got it? Good. Stop that for a second.